So our final talk for this session is given by Anindya Day, and he's going to be talking about, is your function low dimensional?
Thanks. So this joint work with Elkanan Mossal and Joe Neiman. So I assume having the last talk means I can go for as long as I want. It goes both ways. Okay, so I'll start with something which I hope is at least familiar to some of you. Okay, so I'll start with the concept of Juntas, which is a very, I should be here. Okay, which is a very standard concept in Boolean function analysis. A Boolean function, which is a function taking plus minus one value on the n-bit hypercube, meaning the inputs are n-bit strings, is said to be a junta if its value depends on relatively few coordinates of x. So the canonical example is a dictator function, which is just a function of one bit. That is, f of x is just some ith bit of x. A k junta is a function which is just depends on k bits of x. And an example of a not a junta is a majority function because it literally depends on all the bits. Okay? And there's a very standard notion in complexity theory, computation learning theory, and so on. So a lot of the motivation complexity theory came from probabilistically checkable proofs, but at least another motivation comes from the notion of feature selection in machine learning. So think of that you have come up with a model on n bits, and you want to know that maybe while the model as such, it looks like it depends on all n bits, maybe it is the case that it actually depends on only very few bits, and you want to know if there are few relevant variables which determine the function. You want to know if this is the case or not. And so there's another motivation for studying juntas. And again, as I said, it's studied in many, many different ways in complexity and learning theory. And property testing, which is the focus for this talk. So what is property testing? In property testing, you have an oracle access to a function, so the algorithm can query the function at any point and get its value. And the aim of the algorithm is the following. It wants to determine, so property testing of k junta means that the algorithm wants to determine, is the function a k junta, or is the function at least epsilon far from every k junta, where epsilon far just means that the target function, the function you have been given an oracle to, disagrees with every k junta g on at least epsilon fraction of the inputs on the cube. And you want to say this with high confidence, say at least with probably 2/3. And the metric, the thing you want to minimize, is the number of queries you make to this oracle. Okay. And so property testing of juntas has been a very fruitful line of research in complexity. And maybe the flagship result here is that k juntas can be tested with almost order k queries when you're measuring this distance according to the uniform distribution on the cube. So what I want to say is that when you're saying that f and g are far, you're measuring the distance according to the uniform distribution on the cube. Every point is equally weighted. And the key feature, again, I want you to take away is that the query complexity is independent of the ambient dimension n. So if you are trying to say your function depends on one variable, then the query complexity just depends on one, not on n. Okay. Okay, but a lot of data analysis, we are going to go with this motivation that are there few features which determine the model, or are there many features? A lot of data analysis is not done over the cube, but the ambient space is R to the n. So we are still thinking of functions which take plus minus one value, but the inputs are no longer n-bit strings, but like real valued inputs. And then what's the right notion of junta? So earlier we said junta means it depends on a few variables. But that implicitly assumes that you know the basis of the function. And many models such as PCA, ICA, and so on, the whole thing is that you kind of do not know what the right basis for the function is. So maybe a better notion of a junta when the domain is R to the n is this one, which is what we introduced in this paper, is a notion of linear k junta. As a function on R to the n is said to be a linear k junta if the function just depends on a k-dimensional subspace. So in other words, there are some k orthonormal vectors u1 to uk such that f of x just depends on this projection of x on this k-dimensional subspace u1 to uk. So function is still Boolean, okay? And we want to ask the same question as before, namely, can linear k juntas can linear K juntas be tested with query complexity independent of the ambient dimension n? So same thing that we could do over juntas on the Boolean cube. And how do we measure? Again, we need some notion of distance, between two functions, right? So we need to endow R to the n with some measure. And since we are talking about basis independence, it would be natural to put a measure which is rotationally invariant, which doesn't have preferred directions, and maybe the most natural choice is the standard normal measure R to the n. Okay, so that's what we want to know. You have been given oracle access to a function f. You want to know, is this function just dependent on k directions, or is this far from dependent on k directions, where far between two functions is measured with respect to a standard normal measure? So let me ask a slightly easier question. Can you make k equals 1? Can one linear juntas be tested with query complexity independent of the ambient dimension? And I would like to argue that, as such, this question as stated, you cannot do it with any finite query complexity. Here's the reason why. Make n equals 2, okay? The right-hand picture is a random function on R square. What I mean by a random function is that every point on R square is assigned a plus minus 1 value independently at random. Now, this is not technically measurable, but you can make it measurable after some effort, okay? And the left picture on the left-hand side is a random 1 junta, which means you choose a random line in the space, and every point on the line is again assigned a plus minus 1 value independently at random. And any point not on the line, you just project it on the line and assign it that value. Now, while the left-hand side is a 1 junta, the right-hand side is nothing like a 1 junta, as long the algorithm, which doesn't know what this hidden line is, if it makes finite number of queries, as long as it does not query 3 points which have the same projection on the hidden line, it all looks completely random, and it's learning nothing. Now, this argument can be made rigorous, but the point is that, so with any finite number of queries, you can never distinguish between even 1 juntas and 2 juntas. And the fundamental reason is that you need some sort of a smoothness assumption. I'm not going to get into what the natural notion of smoothness assumption is, but the standard notion in at least Gaussian analysis is the notion of Gaussian surface area. If you come to the poster, I can explain what it is. It's a very standard notion. It's somewhat technical to define, but it's really intuitive notion. So with this, at least I can state the results. The algorithmic upper bound is this, that there's an algorithm which takes 3 parameters, the junta arity parameter k, so you want to distinguish k junta or not k junta, so that number k, an upper bound on the surface area S, and a target error parameter epsilon, and makes polynomial in S, k, and 1 over epsilon queries, and with high probability distinguishes between the two cases, namely, the function is a linear junta with surface area at most S, and the function is epsilon far from any linear junta with surface area at most S times 1 plus epsilon. Don't bother about this S times 1 plus epsilon. It's a technical requirement you really require, but just basically it makes polynomial in polynomial number of queries in the 3 relevant parameters, the arity parameter, the error parameter, and the surface area bound, and says is the function is a linear k junta or it's epsilon far from a linear k junta. If you haven't seen the notion of surface area before, it might look like, okay, it's an artificial parameter somehow, but turns out that it's important in the sense that there is a lower bound that any non-adaptive tester, and ours is a non-adaptive tester, any non-adaptive tester, even distinguishing between 1 juntas and 2 juntas, must make S to the 1 over 10 query. So this parameter dependent on the surface area, this is quantitatively and qualitatively tight up to at least polynomial factors. You can't do better. If you switch to non-adaptive tester just means that the queries that the algorithm makes to the function is not dependent on any of the answers. So at the very beginning, the algorithm can decide what points the algorithm will query the function at and then get the answers. It doesn't, the answers are not, the query points are not determined by the answers. Let me not get to a third upper bound. It doesn't mean, it's complicated to explain. I guess I'm out of time. 1 minute, okay, great. So let me try to explain at least a high-level idea. Okay, here's a high-level idea. You're trying to decide if a function is just dependent on k directions or not on k directions. What's the obvious thing to do? Well, assume the function was differentiable. It's not, but you can maybe smoothen it out somehow and make it differentiable. If the function was differentiable, here's an idea. You could have evaluated the gradient of the function at several places. If the function is just dependent on k directions, you evaluate the gradient at k square places. All these k square gradients must lie in a k-dimensional space. And hopefully, with some math, you can prove that if the function is far from a k-junta, this is not going to be the case. The big, and this can be formalized, it's not too hard to do. The big issue is that you cannot evaluate the gradient of a function. The gradient is an n-dimensional vector. You have only constant number of queries. You cannot even get those many bits of information out. But then you think about it, wait a minute, I'm not trying to evaluate the gradient. I'm just trying to evaluate, do the gradients lie on a k-dimensional space or not? So you're trying to evaluate the gram matrix of the gradients. And this gram matrix can somehow implicitly be evaluated essentially by relying on this integration by parts formula in the Gaussian space. If you have seen it, great. If you have not seen it, this is what underlies like Stein's method to prove limit theorems in probability. I am sure now I'm out of time, so let me conclude now. Thanks.
Okay, yeah, questions.
Yeah. You can't identify the orthonormal vectors because, again, the orthonormal vectors, even a single vector is an n-dimensional thing. So you cannot make constant number of queries and identify that. However, what you can identify with like constant number of queries, just without any ambient dimension n, is what the function is up to the rotation. So you can say, oh, this is a function, this is an and function, or this is like, you know, an intersection of two half spaces at an angle pi over 3. You can identify the function up to rotation, and this is pretty much the best you can do without explicitly identifying the directions, and that you cannot do.
Okay, if there are no more questions, let's thank this speaker again.